All right, let's talk about something truly epic. One of humanity's biggest, most audacious dreams, interstellar travel. We're going to break down a real plan that could send a probe to another star system, not in thousands of years, but inside our own lifetime.
So let's just start with the big, hairy problem here. The nearest star, Proxima Centauri, is more than 4 light years away. That's a 40 trillion kilometer gap. I mean, that number is so big it's almost meaningless. How on earth could we possibly build something to cross that insane void?
Well, if we took our very best rocket technology today, the stuff that gets us to Mars, and pointed it at the nearest star, that journey would take about 80,000 years. Think about that. 80,000 years ago, our ancestors were just starting to leave Africa. Yeah, that's just not going to work.
But what if I told you there's a plan to cut that down to just 20 years? That's what changes everything. It's a concept that doesn't rely on carrying fuel, but on being pushed by light itself. So how is that even remotely possible? Let's dive in. Okay, so to really get why the new solution is so radical, you first have to have a deep respect for the problem. The scale of space is just brutal. It creates this tyranny of distance that our current rocket tech just can't overcome. This right here puts it all into perspective. A trip to our next-door neighbor, Mars? About 7 months with a standard chemical rocket. Using that exact same tech to get to Alpha Centauri, the travel time balloons from months to tens of thousands of years. We're not just in a different ballpark, it's a completely different sport. And this quote from the research really gets to the heart of it. Chemical rockets are stuck. They get their energy from breaking chemical bonds, and there's a hard, physical limit to how much energy you can get out of that. To get to the crazy speeds we need, a real chunk of the speed of light, we need about 1 billion times more energy than chemistry can offer. The only way forward is to ditch chemistry and embrace a new tool, electromagnetic acceleration. So the bottom line is, we need a totally new kind of engine. And the proposed solution is, what if you just left the engine behind? Instead of burning fuel on a rocket, the spacecraft gets pushed by an unbelievably powerful laser beam fired from Earth. Now, I know what you're probably thinking. This sounds like total science fiction. But here's the thing. This whole concept is actually grounded in some serious engineering and economic models. It's not just a dream. It's a real proposal with specific cost targets for all the key parts needed to actually pull it off.
And this is the beast that would do the pushing. It's a phased array, which basically just means thousands of lasers spread out over a 10-kilometer area, all firing in perfect sync to create one single colossal beam. We're talking 50 to 70 gigawatts of power. That's more than dozens of nuclear power plants combined, all focused onto a single, tiny target for a few minutes. Just wow. Okay, so you have this ridiculously powerful laser. What in the world can you actually push with it? It can't be some big, clunky probe, no. It has to be impossibly small and light. So small, it fits on a single microchip. Meet the Starchip. You know how the supercomputers of the 60s now fit inside your smartphone? This is the exact same idea, but for a spacecraft. The whole shebang, cameras, power, communications, thrusters, all of it shrunk down and baked onto a silicon wafer that weighs just a few grams. And again, this isn't just a fantasy on a whiteboard. We're already doing this kind of thing. Tiny, functioning satellites called picosatellites, like the Sprite shown here, have already been built and tested in orbit. The Starchip is just the next logical step down a path we're already walking. Now, this tiny chip is attached to a light sail. It's about 1 meter wide, but it's only nanometers thick. You can think of it as a hyper-advanced mirror, made of these special dielectric materials. They are engineered to be almost perfectly reflective, but only to the laser's exact color. This is absolutely crucial because it maximizes the push and stops the sail from absorbing a ton of heat and just vaporizing instantly. So we've got our giant laser array on Earth and our tiny Starchip waiting in orbit. Now for the main event, the launch. And this part is incredibly short, unbelievably violent, and it's where the probe gets all the speed it's ever going to have. It all happens in less than 10 minutes. The gigawatt laser locks onto the sail. For 9 solid minutes, a constant stream of photons, light particles, slams into it, pushing it harder and harder. It accelerates furiously until it hits an incredible 20% of the speed of light. And then, just like that, the laser turns off.
The push is over and the Starship starts its long, quiet 20-year coast to Alpha Centauri.
To give you a sense of just how insane the forces are here, look at this. An astronaut on the space shuttle experienced about 3 Gs during launch. The Starship will endure a peak acceleration of around 20,000 Gs. It's a force so extreme that pretty much only a solid little microchip with no delicate moving parts could possibly hope to survive it. Once that brutal acceleration is done, the Starship's mission enters a new phase. For the next 2 decades, it has to survive a very long, very lonely, and surprisingly dangerous trip through the interstellar medium, that near-perfect vacuum between the stars. So what's the big danger out there in the void? It's not space pirates or black holes. It's something way more common, and at these speeds, way, way deadlier. The number one threat is a single grain of dust. When you're traveling at 60 million meters per second, hitting something not small releases the energy of a bomb. A direct hit could easily blast a hole through the chip or destroy the whole thing outright. So how do you possibly survive that? Well, this is where the engineering gets really clever. The plan is to use a bunch of different tricks. They'll fly the chip edge on, presenting the smallest possible target. They'll build in redundant systems, so if one part gets knocked out, another can take over. And they'll use special coatings and spin the craft to help absorb and deflect any impacts. Okay, so let's imagine our Starship does it. It survives the 20-year journey, it weathers the storm of interstellar dust, and it flies by a planet in the Alpha Centauri system, snapping pictures. But all of that work is for nothing if it can't send that data all the way back home. And the solution for this is it's beautiful. The Starship uses its own tiny 1-watt laser to send the signal. And for its antenna, it uses the exact same meter-wide sail that got it there in the first place, now acting like a dish to focus that weak signal into a tight beam aimed right back at Earth. This last step is maybe the biggest challenge of all. It's a massive signal versus noise problem. That same 10-kilometer laser array on Earth has to switch roles. It stops being a transmitter and becomes a super-sensitive telescope. Its one job is to pick out that tiny 1-watt whisper from 4 light-years away and filter it out from all the background screaming of the cosmos. And that really brings us to the final thought. After all of it, decades of planning, building, and waiting, we get that signal back. Maybe it's a blurry image of a planet orbiting another star, the very first close-up picture of an alien world. That image would finally answer the question, what does it look like over there? But just imagine the thousands of new questions it would force us and the next generation of explorers to ask.